what is hypothesis testing? Well, it's just a formal way of doing what we just did. Right? We sort of had this idea of like, well, I got this drug and I want to convince you that it works. So I did a test, but it didn't seem very convincing. So we had to think about it in a different way and look at it relative to a sampling distribution. So we start with this hypothesis that subjects are normal. So if we assume that subjects that like IQ Plus didn't work, we expect them to function in a way that normal participants, I use the word normal very loosely, like in quotes, typical subjects would respond. And that's really what we do to define the null hypothesis. What would we expect if nothing happened? If IQ Plus didn't work, what would we expect subjects to look like? We do that, we find what normal subjects do, what they look like, and then we take a sample and do something to them, like in this case, give them IQ Plus, and we compare our subjects to the standard of what normal subjects look like. We figure out what normal subjects, normal samples look like, and we compare our sample to that normal. And if our sample seems different than normal, we're going to assume that whatever we did to them worked. In this case, we give them IQ Plus. If our subjects seem just like the normal subjects, then we're going to assume that they got there by just random variability alone, and that IQ Plus in this case didn't work, if that's what occurred. All right. So we're going to do things like we're going to define the null hypothesis, which means you're going to decide what you would expect to find if the null hypothesis were true. Look at what you actually found, and then reject that null if what you found is not what you expected. I'm not going to actually go into this article, but you can click on it if you like in your notes. It's interesting that this idea of if you're like me, but cracking your knuckles, did it my whole life. My parents are always like, don't crack your knuckles, it's going to give you arthritis or whatever thing you're told, that's going to affect it. And there was actually somebody who did this thing like for years and years and years. I want to say like it was like 60, so it was like probably close to 60 years. Cracked the knuckles on just one hand and didn't crack the knuckles on his other hand. So he's using his hands, one hand as sort of the control for the other. And there was, after years of cracking the knuckles on one hand, not the other, there was no difference in the two hands. Anyway, so it's interesting to figure out this idea of sort of testing a null hypothesis, that something you've been told forever, right? That cracking your knuckles is going to cause arthritis. This person sort of tested it out and couldn't reject that null, that cracking your knuckles doesn't do anything. It actually is doesn't affect you in any way. Anyway, so these are the hypothesis testing steps. You're going to state the null, which we typically call H0. Sometimes you hear it called H0. You got the alternative hypothesis, which is sometimes called the research hypothesis, which is H1. We're going to figure out, we need to decide on our alpha level. So this is where you have to decide what level do you think of when it comes to sort of unlikely or unusual. Now I'm saying you're deciding on it, but for the most part, your decision is going to be something like 0.05 or less. So you could decide to go to 0.01, 0.001, something crazy. But there's not a whole lot of decisions to be made here, except for in a in a problem, in some of the practice problems, or on a test, you may be told like assume alpha is 0.01, and then you got to sort of change your alpha level. To decide on the type of test you're going to do, and as we go forward, there's going to be more tests, so more of a decision. Based on the alpha and the type of test you're using, you're going to define something called a critical value, and you're going to state a decision rule. You're going to calculate the test that you want. You've already decided on the type of test, so now you're actually going to apply that test and calculate a test statistic. And then you're going to compare the value you get from the test to your decision rule, and you're going to actually make your decision. Do I reject the null, or do I retain the null? And those really are the two different decisions you're going to make. And I'll explain more about that as we go forward. So the null and alternative are always stated in terms of population parameters. We always say like mu equals 0. Right? So our null is that our mu is going to be 0, right? That our population mean is 0. Our alternative then is going to be the sort of opposite, where the research hypothesis is going to be, well, I think the population mean is not going to equal 0. Together, the important thing is together both of these hypotheses define the entire range of possibilities, right? So if the idea is that mu is equal to some number, mu equals 0, that's just one number, well, then the alternative needs to define all the rest of the values. So if this one's equal, this one will have to be not equal. If this one, say, were, I think mu is less than or equal to 0, it gives us a range, actually, let's say less than 0, and the research hypothesis is that the mu is greater than 0. There's a problem here in that, again, it has to define all possible values. So yes, this defines mu by everything less than 0. This defines mu as everything greater than 0. But the problem is, if it comes out to be exactly 0, 0 is not covered. So one of them always needs to include the equal sign, and that one is always the null. So you can always sort of spot the null hypothesis. If you're given statements about hypotheses, the null is always going to be the one that includes an equal sign. Okay, so if you can do this the other way around, mu is greater than 0 and mu is less than 0. Because this is the null hypothesis, this is one that's going to include equals. This is the alternative, so it's not going to include the equal sign. So the null hypothesis is the sort of not fun hypothesis, right? This one's not any fun. It's the hypothesis that our subjects came from a population of normal responders, right? Just that the sample we took from the population, nothing happened to them. They're just like they were when we took them out of the population. Whatever we did to them didn't work, right? So this is the hypothesis that taking IQ Plus has no effect on intelligence. And this is the hypothesis we usually want to reject. Usually we're stating this one because we're doing our research project, our study, to try to reject this very idea. If I'm developing a drug that's supposed to increase intelligence, I don't want people to stay the same. I don't want people to have no change. I want my drug to change them. I want to show that there is some impact of the drug. So I'm trying to reject this very hypothesis. Okay. The null hypothesis always specifies a single value. It means it has some equal sign in it somewhere, like I said a second ago. So the null is the one that's always going to have an equal sign. And this is where basically we're saying that nothing happened. There's no difference between our sample and the population. This is where we're saying the chance, random chance, is a good explanation for the results. That our sample got to its mean based on random chance. That seems perfectly viable. Another way of saying this too is that your sample statistic, meaning your mean from your sample, doesn't differ from your hypothesized population parameter. So again, our hypothesized population parameter was 100. So if we were to retain the null, to keep this null, we're basically saying, well, the mean of our sample wasn't different from that hypothesized population value of 100. Right? That's what the null hypothesis is doing. The research hypothesis, sometimes known as the alternative hypothesis, this is sort of the fun hypothesis. Often, this is the one where it means there's something happened. There was some action that occurred during the study. So it always specifies a range, so it's not going to have an equal sign in it anywhere. It's always going to be some kind of inequality, either greater than, less than, or not equal to, one of those three. It says that something did happen. There is a difference between your sample and the population. It says that random chance alone is not a good explanation for your results. This is where you get this word significantly. So your sample statistic differs significantly from your hypothesized population parameter. And the word significant has confused people quite a lot for many, many years, decades, because it doesn't mean importantly or something like that. It just means literally if it is a significant difference, it's the same thing as saying, well, it has a low likelihood of occurring by chance. Right? The chance of getting this value based on random variation alone is low. That's all significance means. So your sample statistic differs, right, in a way that is less than 5% chance from your hypothesized population parameter. So don't read too much into significance. Significantly does not mean importantly or something like that. It just means, or substantially, it just means that the chance of it happening by chance alone is very low. When we talk about hypothesis testing, the one thing to remember is it's all probability. Everything we're talking about is in terms of probability. What is the chance, the likelihood, the probability of something occurring? Nothing's ever done in any concrete way where you know with 100% certainty. There's always some level of uncertainty. And because of that, we have to make decisions in this uncertain process. So we're using the statistics, like I said in the very beginning of the session, that this is not a math course, it's a course on decision making. That we're going to use these steps, these processes, to try to better inform our decisions. It doesn't mean our decisions will be correct, it just means that they're informed. So just because your decision is informed doesn't mean that it's infallible. So we're going to use steps like the hypothesis testing steps and all the tests we're going to talk about to better inform our decisions, but we still have to make a decision, either in favor of the null hypothesis, we're going to decide that nothing happened, or we're going to decide that something did happen and sort of reject that null hypothesis and think, well, no, I think IQ Plus really did work. And it's going to be based on those steps and those tests. So because we're making decisions, that means we're likely to make errors. We're going to make the wrong decision at times. So there are two different types of error, type 1 and type 2. An easy way to sort of keep track of them is a type 1 error is known as a false positive. And a type 2 error is known as a false negative. Okay, so a false positive, you go into the doctor, doc takes some blood, do a blood test or something like that. They come back and tell you that they think you have cancer. Okay, that's scary news and stuff, but then they do further tests and confirm that in fact you don't. So that first test was a false positive. It told you that you had something you did not. So the reason why it's called a false positive is because the null hypothesis is you don't have cancer. Right? So null is nothing's happening, right? So the null is you don't have cancer, and yet the test came back and told you the likelihood is you did have cancer because the test rejected that null. It told you there were signs that that null hypothesis wasn't true. The fact that you didn't have cancer was false. So it's a false positive, meaning that it comes back and tells you that something's going on when really there shouldn't be. The rate of this, because of how we typically do everything, is roughly 5%. We're going to get 5% false positives. It's just how it's going to be. So if I do a study 100 times in which the null hypothesis is true, meaning that nothing's happening, right? IQ Plus doesn't work. Right? If that's true in reality, I'm still going to get 5 of those. 5 of those studies are going to come back and tell me that IQ Plus does work. So I'm going to get 5 false positives, even if the null hypothesis is true. So a false negative is the opposite. This is where something is happening, right? Something did occur. So this is where you really do have cancer, but they give you a test and it comes back and says you don't. So it tells you to retain the null. The null means nothing happened. Retain the null, even though you probably shouldn't, or you really shouldn't be retaining null because it in fact is false. So a false negative is where you the alternative hypothesis is true in reality, but you retain the null. You believe the null is true. This one's not as easy to control in terms of the rate. We'll talk about why in a second, but it's not always going to be just 5%. We want to typically have a false negative rate that's like 0.2 or less, but there's things we can do to control that, but it's not always just straightforward. We don't just say, I'm going to set it at 5% the way we do with alpha. Then you get things like critical values, where we take our 5% alpha level and we're going to convert that. We want to convert it over All right, we want to convert it to an actual value. We want to convert it to a score, right, in our distribution. Right? We're trying to figure out some way to make 5% into something useful. We want to convert it over to some kind of score and distribution that we can use to make our decision. So like in our case, we converted that 5%, we could convert the 5% over to a point in the IQ plus distribution where if our IQ plus is higher than that number, we're going to reject a null. But if it's lower than that number, we're going to retain it. So these are sort of like lines in the sand that we draw to say, look, if you go past this, we're going to reject the null. But if we stay on this side of that critical value, we're going to retain the null. And it's going to affect our decisions. And it's also affected by whether or not we want to do a one or two-tailed test. Do we want to look in both sides of the distribution? So think about IQ plus. Do I care only about values? So this is my critical value. Do I only care about, this is our 5% here. Do I only care about values that are above on this side like this? So if this is our population mean of 100. Do I only care about sample means that are above a critical value that way? Or do I want to look on both sides of the distribution? Or here I'm going to cut, this is now going to be, instead of 5%, this is going to be 2.5% and 2.5% here. So I'm taking my 5%, I'm just splitting it up into the two halves of the distribution, because really, if this is my mean of 100, I now care if I'm above the critical value this way. This is one critical value, this is another critical value, just the negative of it. Do I care about whether or not values go to the extreme on either side? This is a one-tailed test because it's only in one tail, where this is a two-tailed test because it is looking on both sides of the distribution, and you could reject going either way, either direction. So this is a one-tailed versus two-tailed. It really just means are you wanting to test whether or not the change in your sample is going in one direction, or can it be changed in either direction? Now for IQ plus, two-tail doesn't make a whole lot of sense. It's called IQ plus, not IQ minus or IQ change or something. So the idea is that I typically would want to likely do a one-tailed test to see if my scores are going above, right? If my scores are actually going above a critical value and actually affecting IQ in a positive way. Right? But there could be other things like, I don't know, let's say if you're instead of IQ plus, if I were to give people like Adderall or Ritalin or something like that, does that actually affect their IQ? And I may not have a specific hypothesis. Well, I think if I give the general population, if I give them Ritalin, well, it's probably going to change their IQ. It's probably going to affect the way their ability to respond to an IQ test. But I don't know if it's going to improve it or make it worse. Because for people that actually have ADD or ADHD, it's likely to improve their scores. But people that don't, it may actually make them a little bit loopy and make their scores worse. So I may, if for something like that, I may want to use a two-tailed test because I'm not certain which direction it might go. So everything that we're doing is going to be done with some kind of probability statement. That's the sort of unsettling part. This is the reason why I say this is not math. Math is usually much more certain than this in terms of coming up with an answer. This is really more about decision making. So you decide on the odds, on the likelihood of casting your decision in favor of the null or the alternative hypothesis. And even after you decide, you're still never certain if you made the right decision, at least not on one study. So oftentimes that's why people do multiple studies, and when they get the same results repeatedly, they start to become a lot more certain about making the right decision. All of your choices are based upon probability distributions, like these sampling distributions, so nothing's ever proved, at least, again, not in one study. So oftentimes it takes a lot more time to develop, to add on more and more proof for something to be sort of really there. When we test a hypothesis, we're going to draw a conclusion, either correct or incorrect. So these are the two types of errors we were talking about before. Type 1 errors reject the null hypothesis when it's actually correct. So in reality, nothing happened, but we reject it. We think that something did happen. That's a type 1 error. In type 2 errors, you retain the null hypothesis when it actually is false. So here, something did happen, like IQ Plus actually worked, but we conclude that it didn't, and we retain the null hypothesis, this idea that the sample is no different than a population. So again, this is the false positive. This is the false negative. You don't have cancer, but you're told you do. You have cancer and are told you don't. And one thing that's interesting about this, especially thinking about cancer or any kind of illness really, you start thinking about, well, what type of error seems worse? So is it worse to be told you have cancer when you don't? Or when you're told you don't have cancer when you do? Now, when it comes to research, when it comes to social sciences and research in this area, we tend to be a lot more worried or concerned about type 1 errors. And the reason why that is because with both of these, it comes oftentimes down to money. Money, resources, time, but in all reality, it comes back to sort of the expense of things and where sort of money and resources get put. If I do a study and I publish the results in a journal that say that some kind of thing exists, that IQ Plus works, well, then more people are going to study that thing, more research, more grant funds, more things are going to go towards looking into that phenomenon. So a lot more time and resources get put into something when really there wasn't anything there. So a type 1 error is oftentimes more costly. However, in medicine, in the medical field, type 2 errors can also be actually they're the ones that can be often costly, because if someone comes in and does a test, say for cancer, and the test comes back negative, well, they're going to proceed to not do anything. They're not going to get any treatment. They're going to live their life sort of normally, and their cancer is going to progress and get worse. So by the time they actually catch that they actually do have cancer, it's actually going to be a lot more treatment, a lot more expensive, lots of things. The chances of survival, all kinds of stuff are going to get worse. So type 2 errors tend to be a lot worse in the medical field, and they tend to try to prevent type 2 errors more. And they do that by allowing more type 1s. And that sounds kind of strange, but I'll give you an example. So I have 2 kids, and in both cases, there's usually early on, you do blood tests when women are pregnant. One of them, I think it's called the AFP. It's something like alpha phenyl protein or something like that. I always forget the terms, but it's something they detect in a pregnant woman's blood. If it's high, it tends to indicate the potential for birth defects, things like spina bifida, or there's some other ones too that I can't recall. But with both kids, my wife's test came back positive, that the alpha phenyl was high, and which indicated that there could be problems, birth defects and things. And usually what that means is that you then go on to do something like an amniocentesis, which is like when they do the needle, and they draw out spinal fluid. So with both kids, came up positive, so we ended up doing the amnio to figure that out, and the amnio then confirmed that in both cases there was no problem. So with that AFP, that first test, they allow for a very high type 1 error rate. I mean, it's like 20%. They allow there to be a lot of false positives, because the more false positives means that they'll avoid making type 2 errors, making false negatives. It would have been a lot worse if the test had come back negative, and as we progressed into the pregnancy, found out that there was a problem like spina bifida or other birth defects, that at that point would have been harder to sort of figure out. It would have been too far along in the pregnancy to do anything. And to do anything, I mean to decide to terminate or whatever. The decision would be, the process would be too far along to making those decisions, which is why they want to figure that out early on and make sure that there's a higher type 1 error rate so that there's a lower type 2. All right. We can think about those things together. So let's assume IQ Plus really has no effect on intelligence. So assume we conclude that IQ plus does work. So IQ plus really doesn't do anything. You remember we said that there's like a 2% chance that we could get a sample size with a mean of 106. Well, what if we just happen to get one of those? One of those rare occurrences could happen, which means we would reject the null hypothesis even though we should have retained it, even though IQ plus didn't work. So this is a type 1 error, and the probability for that is set at alpha. Whatever we decide alpha is, that's the likelihood of making a type 1 error. Therefore, the probability of type 1 error is 0.05 because that's what we decided, and that's the sort of convention. For type 2 errors, it's different. So assume IQ plus does make a difference. It actually does work. So let's say we took a sample size 25. Now remember, we can get, there's a certain range of scores that we'd expect to occur by chance, right? So let's say, here's our mean. We just happen to grab a sample that's on the low end, right? Now they're rare, but it's possible. We give them IQ plus, and IQ plus actually does shift their scores up to here. It does actually make them smarter. It gives them higher IQ. But because of where they are now, they look like they're right around the average. So it's going to look like IQ plus didn't work. Right, we took a low scoring sample and brought them up to average, but based on our test, we're not going to see that. All we're going to know is, well, they look average, so they look like everybody else, so it looks like IQ plus didn't work. Okay, so in that case, IQ plus works, but we're going to conclude that it didn't, and that's a type 2 error. All right, this is it's called a type 2. It's usually denoted by beta. So we got an alpha probability and a beta probability. Alpha being type 1, beta being type 2. We can't really set beta easily. We'll talk more about that later on. And there's a thing called power that's called, it's 1 minus beta. So whatever the probability of beta is, if we take 1 minus that, that's the power of the study. So this is the probability of correctly rejecting a false null hypothesis. So in this case, the null is false. This is the probability that we're going to reject it. So this is a good thing, right? So this is the likelihood that if the alternative is true, that we're going to decide that it is true. So let's look at this in a sort of context. So this thing, as is noted up here, is called the confusion matrix. This is not a name I made up. This is what it is referred to, confusion matrix, because this can get confusing. And there's even times when I need to sort of write this down to sort of figure things out sometimes. And I know the colleagues that sometimes will struggle with this idea because it can get confusing very fast. So there are two things going on in any study. There's reality, right? And the reality is what we don't know. So we're trying to do the study to try to figure out reality. We're trying to learn more about reality by doing the study. So you have reality, which is either the null is true, nothing's happening, nothing occurred, or the alternative is true, something did happen. In our example, the null is IQ plus does not work, or IQ plus does work. Those are the two realities, right? Either IQ plus doesn't work, or IQ plus works. Those are the two. Now, we're going to do our test, right? So we're actually going to apply our, we're working towards a one sample test that we did. We took our means and compared to the population, so one sample test. We're going to do our test. We're going to look at our sample. We're going to do our test, and we're going to come up with one of two decisions. We're either going to decide that nothing happened in favor of the null hypothesis, or we're going to decide that something did happen, and we're going to decide in favor of the alternative. So those are the two decisions we have. These are the two realities. Based on the fact we have two realities and two decisions, it creates four different outcomes. There are two that are good and two that are not so good. So let's talk about the two that are good first. So if, in fact, nothing happened, IQ plus doesn't work, and we decide that it doesn't work, that's a good decision. It's not very interesting. It's not very fun, right? IQ plus didn't work, and we do a study, and it comes back and says, yeah, IQ plus didn't work. Okay. So this is 1 minus alpha. That being said, that means we have roughly 95% chance that if the null is true, that we're going to decide in favor of the null, right? Because alpha is 0.05, 1 minus alpha means 0.95. So the other place we want to be is that if in fact the alternative is true, right? So if IQ plus really does work, we want to be able to find that it works. And that's this 1 minus beta. This is that power region. So this here is the place that, you know, if we're doing a study and I'm trying to develop a drug, this is the place that I want to be. This is the sort of power region, okay? It is the 1 minus beta. It's the probability that if, in fact, IQ plus works, this is the probability that I'm going to find that it works, okay? So then we have the two errors. If the null hypothesis is true, but I decide in favor of the alternative, that's type 1 error, right? Nothing's happening. I think there is something happening. That's a false positive. The other side, something happened, IQ plus works, but the test comes back and tells me that it didn't. That's a false negative. So one thing to keep in mind is that only one reality can occur or another. Like we can't have both realities, which is why if you look here, looking at the numbers, if the null hypothesis is true in reality, well, I have my two choices, but both of those are going to add up to 1, right? Because this is the only reality, so my choice is going to be covering 100% of those choices. On the flip side, if the alternative is true, whatever type 2 ends up being, in this case it just happens to be 0.16. I'm just putting numbers in here. 0.16, I didn't set this. This is based on a couple different things. So if this type 2 error is 0.16, that means that the power is 0.84. Because these two have to add up to 100%. Because if the alternative is true, then both of these need to add up to 100%, because those are the two choices, and this is the only reality. Which is why you get interesting things like, if the alternative is true in reality, you can't make a type 1 error. Right? Because if this is true in reality, only these two scenarios now matter. So I can only make a type 2 or power, that's it. If the null is true in reality, I can't make a type 2 error. Because the null is true in reality, these two are the only choices that come into play. Right? Because if the null is true, the idea of falsely rejecting, right, of keeping a false null doesn't make any sense. Because if the null is true, I can't get to a point where I'm keeping it by accident. Keeping it is good, right? So if the null is true, these are the only two outcomes. The alternative is true, these are the only two outcomes, right? That's why they both add up to 100%. It seems like it'd be like, how do we get 200%? It's not, they don't add up together, it's just we only have one or the other. If we assume this is true, these are the outcomes. If we assume this is true, then these are the outcomes. So like I mentioned before, critical values, these represent the point at which we decide to reject a null hypothesis. So we might decide to reject a null when the probability of the null is less than 0.05. When I say might, you're going to. That's the typical value. So our test statistic has some value with a probability of 0.05, so we're going to figure that out. We're gonna figure out, okay, what Z-score do we need to have in order to get to 0.05, or what T, or what F, or whatever, and we're gonna find a value that's gonna be the cutoff. Those are the critical values. So reject, when we see that value we're talking about in that distribution is the critical value. That's what we're gonna be talking about as we go further. One or two-tail test. Two-tail test rejects the null when the obtained value is too extreme in either direction. So either too high or too low away from the mean, away from the population value. You're going to decide on this before even collecting data, right? You don't like decide on the tails once you have the values and stuff in your data set or whatever. A one-tail test rejects null if it's only too high or only too low. So there's pluses and minuses to each one. If you're doing a one-tailed test, you're putting all of the type 1 error, all the alpha, into one tail, which means the critical value is a little bit smaller, a little bit easier to get to. So let me show you. So the value at, if this is 5%, right, whatever this critical value is, if I do the same thing at 2.5% and 2.5%, this value is going to be closer than this value is. It's going to be farther away because this has all 5% in one side, and this only has 2.5% on this side. So the critical value is going to be a little bit smaller when you do a one-tail test, but if you do a one-tail test and you hypothesize wrong, like I think the drug is going to make people smarter, when in fact they take it and it makes them less smart. It actually hurts their IQ. Well, I have nothing on this side. There's no probability on this side of the distribution to reject that. So I'm just going to come back and say, well, I didn't reject my null. Which is fine if that's what you want. But here, this actually allows you to have some probability on this end so that if what you do actually moves them in this direction, you can still reject the null hypothesis based on that. So even though a one-tailed test may be a little bit easier to reject, that only helps if you hypothesize in the correct direction. A two-tailed test will allow you to reject a null regardless of which direction it goes in. So if you don't really have an idea of how the mean should change, two-tailed tests will likely be better. So it's a trade-off. A little bit harder to meet the criteria, but you get protected going in both directions. This one's a little bit easier, but you have to know enough to be able to guess that the mean will change in the correct direction. So like a one-tailed test would be, I'd only reject the null if IQ plus shows an increase in IQ. All right, so I probably wouldn't expect a reduction, therefore no point in guarding against it. And even if it did reduce, if I had some significance going, or if I had a mean that brought the IQ down, I probably wouldn't want to reject it, even if it went that direction, because it's called IQ plus, right? I only want to test for the drug increasing IQ. So a two-tail test, if I was going to do a two-tail test version, I would reject the null if IQ plus group has a mean that is substantially higher or lower, which in this example seems kind of odd, but I could do that. And just to see if the drug is actually changing people's IQs in one direction or the other in a substantial way, I could actually test for that by doing a two-tail test. So the way, just to illustrate quickly how like alpha and power and these kinds of things sort of work together. If I were to do a one-tailed example, okay, so with a one-tailed example, we need to look at just focus on the top part for a second. If we assume that the null hypothesis is true in reality, I need to figure out, okay, well, what does 0.05% look like in that null distribution? So here I have a mean of 100. Standard deviation of 3 because we figured out that the standard error for the distribution was about 3, which we did from that simulation. So I know that means change about 3 units. So I can look up on a z-table. I can figure out, okay, well, what value do we need to corresponds to about 5%. So the way I figured that out was, if you look at 0.05 on a t-table, it comes out that I think I have it on here, that the z for that comes out to be a one-tail test. I just happen to know. If you look at a z-table for 95% or 5%, because remember this is 95% this way or 5% that way, the z that corresponds to a 0.05 is 1.645. Okay, in the t-table, in the z-table, it's either going to be 1.64 or 1.65. They both are sort of right close to 5 or 95%, depending on which one you want to look at. But neither one of them are exact, so you can use either one of those and it's fine, but the actual value ends up being 1.645. Okay, so 1.645, you're like, well, what does that do for me? Well, let's figure out what does that look like. So 1.645, 1.645 corresponds to what? Well, so I want to convert that over to our distribution here. Take 1.645 times 100, no, that's not right, 1.645 times 3, because 3 is our standard error, equals to 4.935. And I'm going to add that to 100 to give me an actual IQ score that corresponds to 5%. So this is our critical value. This decision axis, this line, represents the critical value. At what IQ, right, what IQ level would I make the decision to deciding that IQ Plus works versus it doesn't work? Well, it corresponds to 104.935, or roughly 104.94. Yeah, so 104.94 is the critical value. This represents the 5% that I was talking about before, and because 5% corresponds to a Z of 1.645, I converted that over to an IQ, taking 1.645 times 3 plus 100, and I got 104.94. All right, so that means this is the 104.94 is the cutoff criteria in this distribution. That's based on the null hypothesis. Okay, so if the null hypothesis is true, mean of 100, I'm going to get into the rejection region, my type 1 error region, 5%, if my sample mean goes above 104.94. Right, so this thing here, this value corresponds to that 104.94. It also corresponds to a Z-score of 1.645. Both of those things are true. This is just the raw score that it corresponds to, and this is the Z-score that it corresponds to. If I have a Z-score that goes above 1.645, I'm going to reject. And if I have a raw score of 104.94, I'm going to reject above that number. Okay? So then what's the rest of this? All right, so this is true, so we can figure out what the critical value is, where my decision rule is or decision axis. On this side, I'm going to decide in terms of the null. That side, I'm going to decide in terms of the alternative. So now, if I assume for a second that this is true, so I'm switching. All right, so now I've switched over. Now this is the true thing in reality. Well, I have, if it's true in reality, I have my sample that has a 106. All right, there's my sample. So I'm basing on the fact that the reality is 106, right? So the alternative is that I have a mean of 106. I figured out that the standard error was 3 based on my simulation before, so I'm still going to apply that. So I now have a distribution that is centered around 106 and has a 3-unit standard error this way. And the whole reason why I want to set up this null hypothesis up here, so I can figure out where the decision axis is, so that can be projected onto this distribution. So that same 104.94 that we found out was my critical value based on the null, I can project that down into my alternative hypothesis here. And so this is what that number is. So right here, I'm getting my 104.94 value is sitting right there, right? And I projected it down here. So in order for me to figure out what is my type 1 error and my power values, I just figure out, okay, well, where does 104.94 stand relative to my 106? So I took 104.94 minus 106, right? Just took the critical value minus my mean, and got negative 0.353. In the Z table, if I look up the smaller area, the smaller area relative to that number, that 0.353 number, I get to the smaller area as 0.3632. So that tells me that this area that corresponds to type 2 is roughly, it's a 0.3632 area. That's the area of that part. If that's true, then I should be able to take 1 minus that number to figure out that on this side, I have a 1 minus 0.3632 is 0.6368. So it tells me that my power is roughly 64 and my type 1 error is roughly 36. So I can figure that out based on this number. All right, so I used the null hypothesis to figure out where the critical value is. I then projected that critical value down into the distribution based on the alternative hypothesis so that I can figure out where my decision is based on that same critical value is going to lead me either to a type 2 error or to power. That's based on a one-tail test. How does that change if it's two-tailed? Well, if it's a two-tail test, this is going to move over slightly. It's going to go from 5% to 2.5, and then I'm going to have a value on this side. But it means it's going to move the critical value over, which means more type 2, less power. So let's look at how that works. This is the same example, just now if we assume a two-tailed test instead. So, because it's a two-tailed test, the null hypothesis now splits alpha into 2. So alpha divided by 2, I got 2.5% there, 2.5% there. So how would I figure out what number corresponds to there? So if I know that this is my distribution, and I know I have 2.5% there, and I have 2.5% here, how would I figure out what these numbers should be? How would I figure out how to figure out those z-scores? There's a couple different ways of thinking about it. If I take 5% on both tails, that means that the middle of this, right, that means there's 95% in the middle. So 95% in the middle means 47.5% there, 47.5% there. So I could just look for a mean to z value that's roughly close to 47.5%. It's one way. I could look for the smaller portion that corresponds to 2.5%. That's another way I can figure it out. Right? That would work as well. If you're looking at just one side, this would be minus 2%. That means this is really 97.5. So to this point, 97.5% would be this, down to negative infinity, right? Without looking at the two sides, I could look at 97.5% in the larger portion. So I can look at 97.5 in larger, 2.5 in the smaller, or a mean to z of 47.5. All those things should lead me to the same z. And it's just that I would have a positive version here and a negative version there. Right? So I would need two of them to correspond to both sides of this two-tailed distribution. So I want in the larger portion needs to be 97.5. The mean to z needs to be 47.5, and the smaller portion needs to be 2.5. So let's look at that. That's like the easiest, most straightforward way. I needed 0.025 in the smaller portion, a 0.975 in the larger portion, and a 0.475 in the mean to z column. So it looks like this is perfect. So my two values are going to be 1.96 and negative 1.96 because I have one on both sides. So what we can figure out is that based on this cutoff here, right, in the z-scores is going to be a z of 1.96, and realistically there's another one on this side, right? There's another one here, right? That is this is going to be negative 1.96. So we got them on both sides. It's just that because our sample is larger than the mean, we get a positive number. We're not concerned with this one right now, which is why it's not taking part in any of the rest of this. So what matters is I have a positive 1.96. I need to figure out what that would look like if it were an actual IQ test or an IQ value. So 1.96, it's still the same 3 units of standard error. So 1.96 times 3 equals 5.88. And I'm going to add that to 100, because that's the mean. So that's where this 105.88 comes from. Okay, 105.88 is just this 1.96 z-score converted over to an IQ score, so we can figure out what the critical value is. So remember, this line here is our critical value. It's a place that allows us to make our decision. If we're on this side of it, that's the null. If we're on this side, we're going to decide in favor of the alternative. Okay, it just happens to be if the null is true, this is a good decision, that is a bad decision, which is why it's in the type 1 error zone. We know we have a sample with a mean of 106, so we make a distribution based on that, and we are going to figure out exactly where this 1.96 cutoff in Z, or the 105.88, falls in this distribution, so it's somewhere near there. So I need to figure out, okay, well, what does this correspond to? What does 105.88 correspond to when the alternative is true? What does that 105.88 correspond to in this distribution? So it gets projected down into this distribution, and we can figure out that 105.88 minus 106 over 3 is 0.04. When we look at a z-score of 0.04, so here's my z-score of 0.04. It tells me that the mean to z is 0.016. That's not super useful. But the larger portion is 0.5120 and the smaller portion is 0.4880. All right, let's switch back to the drawing again here. So that's where that 0.48, whatever number came from, is that this is the smaller portion. So because we're here, right, just below the mean, this is the smaller portion. So that tells me that this area for B is that 0.4840. That's my type 2 error. And at this side, power, it's going to be 1 minus that, which we figured out here, is 0.516. And that's just the larger portion relative to that z-score of 0.04. And this number is 0.516. Okay. We're not going to spend a whole lot of time sort of talking about power or having you compute a lot of this stuff. I just want you to get the idea of how it sort of works. We could decide on alpha, and our decision about whether alpha is one-tailed or two-tailed does affect power because it actually can shift it one way or the other. And we use the critical value, this decision axis here, based on the null, to project it into a distribution based on the alternative, and then we use that to figure out what the probability of a type 2 error versus power is using that same critical value.